So good afternoon, everybody. Thanks for coming to this Petit Comité Central seminar today. Today we have Lisa Go. Lisa did her bachelor's in the National University of Singapore, and then his master's degree in the University College of London. And now she's doing her PhD in Paris, Paris-Saclay, in the Cosmology Telescope. So Lisa, the floor is yours.
Thank you very much for the introduction. Thank you for allowing me the opportunity. So today I'll be talking to you about constraining constant and tomographic coupled dark energy with low and high redshifts. That's a really long title, but we'll break it down more. So this talk is based on work that was published earlier this year with my supervisor and my collaborator in Italy. So if you're interested, please do check it out. Okay, so this will be the contents of my talk today. First, I'll give the introduction and motivation of what we're trying to do here, and then I'll go into introducing the exact formalism behind what a coupled dark energy model is. And then afterwards, we'll move on to talk about some of the new. So the novel solution that we proposed, which is the tomographic coupled dark energy framework. And then I'll move on to explain methodology, and then finally present some results and the conclusions. Okay, so a bit of context. I'm sure you're all familiar with the accordance lambda-Steelian model, how it's been very efficient and effectively describing our universe today. However, there are still some questions that remain unanswered. For example, what exactly is the true nature of this term that we call dark energy? Makes up like 70% of our universe. Is it just a convenient cosmological constant, or could there be some new physics that needs to be uncovered? Also, I'm sure you are familiar with the two most famous tensions that are present today in the research community: the Hubble tension, so the value of H0 measured between early time and late time probes, as well as the S8 tension, so the measure of how clustered the universe is. And this discrepancy is about 2 to 3 sigma between Planck and large-scale structure measurements. So all these questions lead us to wonder if the lambda-Steelian model is sufficient to explain our universe today. So with this in mind, we choose to look at some lambda-Steelian model extensions. So here we focus on what is known as the coupled dark energy model. So it's a class of lambda-Steelian model extensions that was first proposed in the 1990s, and it was originally proposed as a solution to the coincidence problem. So why is it that the various components of our universe are about the same magnitude today? So like 0.3 for omega x, 7 for omega lambda. So it was first hypothesized to solve this problem. However, from then on, since the next 20, 30 years, it's been extensively studied in literature, both at background and perturbation levels, and also n-body simulations that have been developed in such a framework, as well as spherical collapse model. So it's a very well-studied model, and also has been shown to be able to read the Hubble tension. It was proposed before and independently such an immersion of this tension. And it's one of the few forerunners that is a viable option today with regards to lambda-Steelian model extensions that's still being studied. So with all this in mind, I hope I've sold this idea to you of what a coupled dark energy model is. So we'll dive into what exactly it entails. So firstly, let's start always with Lagrangian. So here we have the modified Lagrangian of the dark sector. So we're focusing mainly on dark energy and dark matter. So here. So here we have the scalar used by, which we assume takes on the form of dark energy, and then it mediates this interaction between cold dark matter particles, which we assume to be fermionic. So we denote them as psi, and they have a mass that is independent. So also here we note that baryons are not coupled, so we assume a screening mechanism, and hence this satisfies solar system constraints. And then we move on to look at the modified energy momentum tensor T mu nu. So instead of it being zero, instead of the right hand side being zero as the lambda CPM, here we have a coupling between phi and cold dark matter. And the strength of this coupling is dictated by this parameter here, beta. So we can express beta as the partial derivative of m, the mass is with respect to phi, and the dimensionless coupling strength parameter, which is the main study of interest in coupled dark energy model. So in this scalar field theory framework, hence dark matter particles will feel a fifth force that's stronger than gravity. So instead of your regular Newtonian gravitational constant, having G effective, that is a factor of multiplied by a factor of 1 plus 2 beta squared. Hence we see that basically this coupling will cause dark matter particles to have a sort of stronger clustering, as we later on in the perturbation equations. And also in previous literature, it's been shown that coupling strength beta is constrained beyond the order of 0.1.
Sorry. Why is the fifth force stronger than gravity? Is it obvious?
So if you have like so instead of your regular G and beta is gone, so
But it could be 0.0001 and being not.
This fifth force is kind of equivalent or it depends on the
Yeah, just looking at the. I was just looking at the equations. I don't know if it's straightforward. That is much stronger than that is stronger than gravity. I mean, is it obvious from what you have in your Lagrangian and tensors and so on that the effective G is stronger than the Newtonian? Is it obvious?
No, it can be slightly stronger or much stronger. It's all dependent on how much beta is. So like
Yeah.
beta is like 0.001, then of course that it's not much stronger. But beta is like 1, then
Okay.
much. Yeah, it's all dependent on what value. But so far it has been shown that it's 0.1 or less, so it's not that much.
Yeah, so well, I could ask at the end before I forget. Is it necessary that the cold dark matter be dynamic or
Not,
not as good?
yeah, not necessarily. Here, the wave formation of
But does it change anything then?
I'm not too sure about that.
Changes the Lagrangian.
Right, well, I'm meaning then the result of the
Dimensions of the
constraints.
Lagrangian are defined. If you change the dimensions of the field, you change the dimension. You change the
Right.
components of the Lagrangian.
No, but then my question was more in terms of observable.
Yeah.
But usually, I think if you are say ultralight, probably you don't have the same because if you have ultralight field, you don't tend to dilute the cluster. But we are getting on top.
Yeah, sorry. It's just, let's just.
So going back now, next we can look at the background evolution equations. So we're focusing all of this in the synchronous gauge. So here we give the evolution equations for the background of the cold dark matter particles, and we see once again on the right hand side the beta term coming out. So then you can see that the effect of coupling, the effect of beta becomes significant, maybe when rho CDM is non-negligible. So maybe during matter dominated eras, we would expect that the impact on coupling is the most evident. And also we can express the density and pressure of the scalar field as such. So it's a sum of phi prime between square plus this potential term. But for simplicity, we assume flat potentials. So phi is not, but in the past there has been studies of cases of exponentials or sort of like stone rules form of the potential for this case for simplicity. Next, we look at the perturbation equations. So here we express the evolution of scalar field, and the fine Gaussian equation. have the data coming out here instead of it being zero on the right side. And then also can express the evolution of the CDM, so cold dark matter density contrast. And here we have a second order ODE for it, and then we see the data coming out here and here. So you can see that the effect of a coupling is that clustering will be enhanced in a coupled dark energy frame. Okay, so moving on, so we've laid out all the framework for the coupled dark energy models, and we've got all the equations out. So next we want to look at what happens if we assume a tomographic coupled dark energy. What does that mean? So in the past, as I've introduced, the coupling strength data has always been assumed to be a constant value throughout cosmic evolution. However, does this always have to be so? You see that actually there is no physical motivation as to why data has to be constant. And also when we look at other coupling paradigms, such as between vacuum energy and dark matter particles themselves, or between neutrinos. So in all these cases, it's shown that varying coupling is actually favored over the constant. So this leads us to the aim of our research, which is to investigate what happens if we allow data to vary throughout cosmic evolution, and how the cosmological parameters, how observables will be affected by such tomographic coupling. And also I've mentioned that DBE frameworks have been able to alleviate H0 tension. So we want to see what happens if we increase these degrees of freedom, and this further alleviate these tensions. Moving on to our methodology. So we propose a new parameterization for data where we express it in terms of redshift. So we have data as a function of Z. And what we did was to bin data, bin coupling, by expressing it as a sum of hyperbolic tangents. So here in this case, we have N, which is the number of bins, and beta I is the strength of the coupling within each bin. And then we can also choose the value of the bin edges, and that's just a smoothing parameter that we set from the sample. So for example, here we have a plot of data being set. So this is a toy model where we assume 3 bins, bin edges of 100 and 1,000, and then we allow coupling to the amplitude of coupling to vary independently of all the redshift bins. So with this setup, we try to calculate the background and perturbation equations from there to see what is the effect of the tomographic coupling on the various observables. So firstly, we have a plot of omega scalar field and omega f. So here what we did was to progressively turn on coupling from low to high redshifts. So here we see, there's a plain green dotted line which denotes lambda CDM, no coupling, and then we see what happens if we turn on coupling progressively to a value of 0.1 at all the different redshifts, and see that actually as we turn coupling on, we see a scaling solution that's reached for omega 5 during the matter-dominated era. So as we've seen from the background equations, how coupling mostly affects is mostly evident in the matter-dominated era. And also, the sum of omega variance and omega cold dark matter decreases due to this increase in omega 5. And then we can also plot the evolution of the Hubble function, basically. And what we see that is when we keep initial conditions constant, H0, so the value Hz on the y-axis actually increases as we progressively switch on coupling at higher redshift. So going from CDM to coupling of 0.1 at low redshifts, and then turn on coupling progressively. So that H0 basically increases in that. Okay, moving on to the perturbation observables. So on the left here, we have the matter power spectrum, and on the right, we have the CME temperature and isotropy. And here what we did was to just turn on coupling at one particular the redshift bin and then increase it to see its effect on the observation observables. So firstly, you see on the left that when you increase coupling from 0.25 to 0.25, the amplitude of clustering enhances, and very much when you use it, like it doesn't go linearly. And also, with regards to the CMB temperature and isotropy, we see the peaks will shift to higher multiples, so higher values of L, and due to the increase in Higgs effect, or RS, the sound horizon. And then we do that for the second coupling bin, and tomographic bin, so 100 per 1000 redshift. And we see once again that the amplitude of clustering is enhanced, although the effect is less than if you turn it on at daytimes. And also the same effect with the CMB temperature and isotropies. And finally, at the highest redshift bin, so that 10,000, so that this has the least effect of increasing the clustering. And also interestingly, we see that the amplitude of the first peak will increase when you increase coupling. And this is due to the increase in your ratio between rho coded matter and beta. Okay, so what we did was to basically first modify our Boltzmann solver, which is known as BLAST, and then we move on to run NCMC to perform a likelihood analysis such that we can constrain coupling and see how this might affect all our other cosmological observables. And what we did was to use different data sets, and from there, based on the data sets, we employed test 3 different parameterizations for our data set. So firstly, we use purely CMB data, and for this, we use the 3-bin models. CMB data, we constraints at higher redshift, and next, we see what happens when we add background data sets at lower redshifts. So we have baryonic acoustic oscillations, type 1A supernova, redshift space distortion, as well as the Schultz prior. So since all these reside at lower redshifts, so what we did was to bin the redshifts at introduce like a finer binning at lower redshifts to capture all these data sets. And finally, we also made use of weak lensing, that's clustering in 3x2 point data. And since all these are low redshift data as well, we only bin it at low redshift since we don't expect much different. We don't expect them to be sensitive at redshifts higher than 2. 3x2 point. Then I'll get to that. Firstly, we look at CMB constraints, so high redshift constraints. So once again, reminding you, these are the redshift bins that we have used, and this roughly corresponds to the era of structure formation, post-combination, and pre-replication. So for this parameterization, we employed CMB data from first the Planck dataset, and as well as the data from the Atacama Cosmology Telescope that came out just earlier this year, as well as from the Southern Telescope, which is also new data. And what we did was to not just simply combine all these data sets, but to consider different scale cuts of these different data sets. So what we did, firstly, is to use pure Planck data, so temperature, process for the polarization data, and then we add on X data, but we cut it at the multiple of 1800 instead of this effect of double counting between overlap between Planck and X. And then we add on SPT data. And finally, we consider an alternative data set where we cut the Planck spectrum at an Lmax of 615 instead. Because this data set has actually shown to lend preference to early dark energy models. So in the past literature, when they use this data set to lend preference towards EV models. So we want to see if this is also the case for couple dark energy models when we compare between the Planck 650 plus that versus if we use more Planck and less accurate. Okay, so this is some of the results. So here we have a plot of the reconstruction of data set in redshift. So here are the upper limits at 95% confidence level for coupling for the 4 different data sets. And also we compare it with the case of the constant coupling, which is purely Planck. And we see that tomographic coupling generally allows for larger values of data. So we compare the colored lines versus black lines. And also one reassuring thing to note that it's still beta 0, so now it's still not ruled out. So the bottom line here is basically just an overlap of all the lower bounds. So we still have the data is still compatible with Planck's. Also now we can also focus on constraints at high redshifts. So focusing on data 3, we see that Planck, purely Planck dataset, as expected, is tightest constraints on coupling at early times, data 3 less than 0.049. And then moving on, at data and SPT data, then increasingly pushes this constraint up. And finally, when we consider a cut on the Planck data, we see that this actually produces the loosest constraints on coupling. So almost one order of magnitude higher than just this Planck data. So we sort of see that Planck data at high multiples gives tightest constraints on data 3, and this is because high multiple data actually fixes the amplitude of the first to high resolution. So this is a change in which data 3 is more sensitive towards, so than expected. Next, we move on to look at constraints on all the different cosmological parameters. So here in green, we have the case of CEN, and then a constant data and all the different data sets for tomographic coupling. We see that here we have the pink bands, which is Planck bifunctional cosmology, and we see that generally within 1 sigma levels, this is the mean and 1 sigma. So they are all generally in agreement with Planck bifunctional cosmology. However, if we zoom in at clustering, so the parameter sigma h, we see that clustering is enhanced with the tomographic coupling model. And H naught, the value of H naught is increased, although this is also due to an enlargement in the error bar. So with respect to alleviating the H naught tension, have we been able to do so? The question is, firstly, we know that in lambda CDM, we sort of having 4.8 sigma tension between the value measured by Planck and Schultz. And then constant coupling case, we see that this actually decreases to 2.9 sigma. However, we note that this is also due to an increase in the error bars, basically. And in the case of the tomographic coupling, we have a slight increase of 0.9 to 0.7, once again, also due to an increase in the error bars of each naught. Okay, next we move on to background constraints. So as I introduced earlier, here we have a 7-bin coupling model where we add on background data. This bin edges were mostly motivated by the redshift ranges of the data we have employed. And so for all the different data sets here, we have PAO from Ross, for DES, and type 1A supernova from Pantheon, and the DES data sets. And we also use cosmic chronometers and RSD data points, and also the updated Schultz prior from the fall 2021. So what we want to do is to combine this area of background data sets with CMD data, but we do so individually in order to understand the individual effect on coupling function. So here are all the different data sets that we have considered. So firstly, we look at combining our background data with Planck plus F1000 800 with SPT. So favorite Planck data, and here PAO, and SPH, which we term BSC, and as our first initial data set. And then we see what happens if we add on RSD data or Schultz or all of them together. And then we consider the other data set where we choose trust the active SPT more and cut out the high multiples of Planck. So we want to see basically what can each data set, background data set tell us about coupling at different things. So here are our results. So here I show the 1 sigma upper limit of all the different data amplitudes, 1 to 7. And then we have also the case for constant data. And we see that across the board, generally, the trend is that coupling is least constrained at low redshifts. So redshift less than 5, data 1, 2, 3 is much less. It can take on higher values, basically, than coupling at redshifts of between 5 to 1,000. So for example, taking this data set as an example, we have at redshifts of less than 1, you can have data is close to 0.146. However, if you look at during structure formation here, so a redshift bin of 100 to 500, you see that the upper limit is basically 1 order of magnitude. Also, interestingly, when we compare between the two different CMB scale types, we see that non-null coupling actually seems to be favored when we choose to trust Planck data more. And this might be due to the fact that we require a non-null coupling to reconcile the tension in H naught. So we see how with non-null coupling we can sort of decrease the value of H naught in the background evolution plots. So when you have a tension between Planck and shoes, you sort of need to have this presence of coupling to reconcile this tension. Okay, so moving on, finally, the last thing we've looked at was to use bit blending to constrain our conductivity model. So this is a new data set that has never been used in past literature. Studies of coupled dark energy. So what we did was to use it to constrain both constant and tomographic models. And here we chose to use a 4-bin tomographic model probed by beat lensing and also your full shape get spectroscopic data clustering, and your cross correlation gets lensing. So when you cross beat lensing and get clustering, you get galaxy density. So to be specific, we use data from the cosmic shear, data from your KITS 1000 survey. Your galaxies basically reside redshifts of 0.1 to 1.2. And then you use some galaxy clustering from your BOSS DR12 data release. And finally, you cross-correlate these two. So you have your KITS galaxies crossed with your BOSS galaxy to obtain your galaxy lensing power spectrum. And then when you combine all these three, we call it the 3 times 2 point data set. Like 2 point statistic, and then like 1, 2. That's your question. So, also one thing to note is that in this case, weak cleansing, cosmic shear especially, is highly sensitive to non-linear scales. However, we do not really have a good model for non-linear scales in a tomographic coupled dark energy model yet. So what we did was to make a very conservative cut at multiples of less than 1,500 to exclude this non-linear scales, not bias out. Okay, so some results. So firstly, we look at our constant case. And here we have the full contour plots for all the different cosmological parameters as well as data or coupling parameter. So firstly, we see that in yellow we have cosmic shear, in green we have clustering, and in blue 3 times 2 point. And you see comparing yellow with blue galaxy clustering 3 times 2 point are very powerful actually, constraining cosmological parameters and your coupling constant, your coupling trend. And this is to report all the different values of data at 2 sigma. So you see going from cosmic shear, you sort of have a limit of 0.064. However, when you use galaxy clustering, this sort of increases by a factor of 5. Okay, next here we look at also the tomographic case. So here we report all your mean and one sigma of your cosmological parameters, as well as the 4 different amplitudes of coupling. And if we zoom in at our results on the coupling constants, we see that going from a constant model, so the blue, to the yellow, which is the tomographic coupling model, we see that constraints are greatly loosened when you use cosmic shear data. So here in the tomographic case, you can sort of have a much higher upper limit for beta as compared to constant. However, this is not the case when you for that's clustering and 2 times 2 point, they remain roughly the same. And also, when you compare between the different tomographic bins, you see that they're not very sensitive towards each evolution between each bin. And this might be because we don't have enough data points within each so galaxy coinciding between each bin. Also, interestingly, if we compare Planck and 2 times 2 point in a constant coupling case, we see that the constraint power is actually very similar or even higher. So our 3 times 2 point, even though it's a low range node, actually gives very tight constraints on all your cosmological parameters as well as your coupling, comparable to Planck. So it's and interesting to note because they have very different systematics and independent proofs of the middle. So this is a very good posture. Also, in terms of the assay function, so if we focus on the value of assay that we obtain, for a number CDM, we sort of have a 3.1 sigma tension from between Planck and 2 times 2 point data. However, in a constant coupling case, this reduces to 1.8 sigma. And interestingly, we keep the error bars about roughly the same magnitude. So this is also a very exciting potential result. Okay, finally, we move on to cannot forget to look at model comparison. So on the Bayesian framework. So first what we did was to calculate your delta chi-squared for each data set. And then here we report the delta chi-square minimum for all the different data sets and models that we studied. So we see that delta chi-square is basically negative. So this means that the data favors a CDE model over lambda CDM. So the better fit CDE basically is a better fit than lambda CDM for the data. However, it's been shown that your delta chi-square is a very rough estimate for such model comparisons. So what we did to be more robust, but to be more robust, also we calculate what is known as the Bayes ratio. So we have to calculate here the evidence, and then this gives a more accurate measure of the goodness of it, because it also takes into account the number of parameters that in the model. It basically penalizes the more parameters that. So when we calculate log B, we have again negative values, but in this case, log B less than -3 for all data sets, which according to Jeffrey's scale, which is basically the scale to measure how well the goodness of fit of your model. This indicates that there is a substantial preference for lambda CDM over tomographic or constant coupled definition. Also because being in the 7-bin data, you are basically introducing 7 extra parameters. So this greatly penalizes the coupled definition correlations. Okay, so I reached the conclusions of my talk. So what I've done was basically to study a graph of lambda CDM models known as coupled definition books. Here we assume that energy to take on a scalar and its interaction between your dark matter particles with the coupling strength beta. So explore constraints on beta. And what we did was to introduce a new tomographic parameterization data by essentially allowing it to vary with redshift in a new logical framework. And we studied 3 different parameterizations for data based on the data set that we have employed. So firstly, only with high redshift, datasets with CMD. We have a Freeman model, and then we saw what happened is we add on background data probes with the 7-bin model, and finally, for the first time, we used deep lensing, galaxy clustering, and galaxy lensing, where we introduced a 4-bin model that is finer binning at no redshifts only. And what we found is that constraints on coupling basically loosen across all datasets compared to a constant coupling case. And also the H0 tension is reduced from 4.8 sigma to about 2.9 sigma. Next to when we add on background data, we see that constraints are looser at late times compared to during the era of structure formation. However, when we include pre-cleansing, galaxy clustering, and 3x2-point data, this actually constraints on coupling at late times are once again very tightly constrained and comparable to CMD data. And also we are able to reduce the S8 tension from 3.1 sigma to about 1.8 sigma. And with upcoming stage 4 surveys like Euclid and LST, actually these low redshift probes are very good in, have shown great potential in constraining such lambda CDM model extensions. Okay, so we've come to the end of my talk, and thank you very much.
Thank you, Lisa. Are there any questions?
Data allowed to be negative? Yeah.
Yes, well, looking at the because a lot of the frames and equations that come from the background, like beta square.
And so when you calculate your audience cosmological constant based on beta, you take the median value of the beta, you propagate these errors, or yeah. So what you take from your fix is beta, right? Is the beta. How do you get from that to I don't know constraints on H1?
Okay, so in the software, the library class we use, we modify the background and perturbation equations, and then from there, give us the natural spectrum, the spin.
So they're simultaneously fit, right?
Yeah.
With the mass.
Other questions? I have one. In the model that you were choosing for lake time, like the binning is like 0.5, 1, 2, and also for the 7.1, why this particular redshifts? Like you were said that it's motivated by the data sets, but like which one refer to?
So for recleansing, basically we saw how we looked at all the different galaxies between 0 to 2, because mainly between 0 to 2, and then we try and see which binning will maximize the number of galaxies. So it's most motivated by the data.
You're trying to have like a similar number of galaxies in the same bin. Okay. Yes. Further questions? So let's thank Lisa again for the talk.
If you enjoyed the video, like and subscribe.